guys, welcome back to another video. So today we're going to be trying a reaction that I think is totally awesome. One of my fellow moderators on Discord, guy goes by the handle B.Shackleford. He posted this on Science Madness and shared it with us, and I just thought it was really cool. What we're doing is we're going to make ethylenediamine, and this is pretty accessible for the amateur chemists because the only things that we need to make this is a strong hydroxide like sodium or potassium hydroxide, ethylene glycol, which as you know is simply antifreeze, and we need urea. And you know, I just thought it was really cool. I've never seen anybody do this before. I will post a link in the video and in the description to the Science Madness post. Other than that, there's really not too much to say about it. So let's just get right into the chemistry here. So what I got going on here is I have, all I had on hand was the 50-50 diluted antifreeze. So I am getting all the water out of it. If you guys are not doing this at home, don't do it with the full strength antifreeze. The only reason that I'm even using this junk right here is because this has just happened to be what I have on hand. So I've got to evaporate down, you know, about half the volume of this to get all the water off of it. So it's going to take a while. So now it's just a waiting game pretty much. I'll come back when this is ready to go. While we're waiting for our ethylene glycol to evaporate down, well, the water off of it anyhow, I just wanted to show you guys some stuff here that I got. Some new toys for the lab. So we got this new vacuum pump. Finally got a proper vacuum chamber so we can do some desiccations that were impossible before. So those are some new toys that I got we're going to be playing with here soon. And we come over here to all the fun stuff. We've got this guy right here, which I don't know if you can read that or not. Focus, god damn it. There we go. So some hydroxylamine. We're going to be having fun with that. I'm sure some of you probably know first thing I'm going to do with that. For those that don't, it'll be a surprise. And then we got this bad boy right here. We're going to be having some fun with this. Make some nice toxic stuff. Well, more toxic than what we normally play with anyhow. So So I got everything reset up here. We're doing the simple distillation step right now. So this is right after hydrolysis of the intermediate product we made. And so you see I've got my magnetic stirring hot plate on the lab jack, and then I've got everything insulated in foil. I took off the climb reservoir. Didn't need that, I didn't think, so I'm trying it without it. If it starts to foam really bad, I can just move the heat out of the way by lowering the lab jack real fast. And so that's how I can control the foaming if that becomes an issue. And then you see I've got my thermocouple probe in the thing, still head there. And we are monitoring that temperature as well as the oil bath temperature on our nifty little 4-channel K-type thermocouple. There it is right there. And if you don't remember from earlier, the top number is the oil bath temperature and the bottom number is the temperature at the still head. We got probably 75 to 80 mils of crude ethylene-diamine after the hydrolysis, and after the distillation, after the hydrolysis, but after the distillation that I did as the last step. The distillation had all but stopped last night when I was doing it, and so I thought that I had gotten out all of the water and ethanolamine azeotrope that was in there, and I pretty much had done so because I distilled a little bit out of that this morning, and I only was able to pull about 15 to 20 mils off of this, which is the stuff that I was distilling when you last saw me. What you're looking at right here, this is actually the Supernatant from, this is what I could not get to distill over. It's what the solution looks like. And this is the Supernatant from the hydrolysis and everything else that we've done so far. And so what occurred here with the distillation, this, I'm not sure what it is exactly. I need to do a little bit of research and figure it out. But that is, is obviously some sort of side product. And that is looking like one of two major side products that this reaction produces. The first of which being the solid that we already filtered off, which is, I'm not sure what the compound is, but if I'm remembering correctly from the paper, it has the same atomic mass value that imidazole has. So you just figure it like it's imidazole, and then you can figure out your stoichiometry from there. Which, if I'm remembering that correctly, I think that might be 86 grams per mole for imidazole. Don't quote me on that. I will put it in the video later on here. What happened is that I figured the way that it was going to happen is that first water would come over, and then at a little bit higher of a boiling point, we would get the azeotrope between water and ethanolamine. And so I had planned just to distill everything pretty much to dryness, all in one pot. And it didn't work that way because, as you saw, my water was only boiling at around 100.5 to 102 degrees the whole time. And this distillation, this simple distillation, I had, an hour and 40 minutes just in the filtration of that, which I'm glad that I did filter that because it gave me a nice looking mother liquor to work with. But what happened is that everything came over at between 100 and 102 C, and by everything I mean the ethanolamine, the water, and the azeotrope. So yeah, that was a little bit surprising. I was not anticipating that. So basically, though, that's a good thing, because what that means, though, is that what we are distilling right now is nothing but water and the I said ethanolamine just a second ago, I think, didn't I? I didn't mean that. I meant ethylene-diamine. I don't know why the hell I said ethanolamine. Sorry, guys. I'm pretty freaking exhausted right now, as usual, but right now it's even more so. Anyhow, yeah, the ethylene-diamine. So now we're distilling nothing but just clear water, distilled water, and ethylene-diamine. Any insoluble salts that we made so far, we got rid of those in the filtration step. So I guess the point is that it worked out well because I just distilled everything until nothing more would come over at 102. The temperature did not even want to climb once it hit 102, so I have no idea what's in this. This could quite possibly be maybe some unreacted ethylene glycol, although I doubt it. It doesn't smell anything like it. However, it does not smell like what our crude product smells like so far, which is a good thing. And what that smells like is a very unique odor. I had never smelled anything quite like it before, and Brother Shackleford was trying to define it for me. And the best he could come up with is it's kind of a combination, at least at this point, between ammonia and something really musty, like mildew almost. And that is pretty accurate. I would basically describe the solution, what it smells like, the solution that we are distilling off right now, which is this stuff right here. If you guys aren't following me, we'll do this very simple. This right here. This is our solution that we're distilling, and it smells exactly like I thought the ethylenediamine would, which again is kind of musty and kind of ammoniacal smelling too. And that's exactly what we want, because right now we did not evolve all of the ammonia gas out of the urea in the initial heating step, and so because we have not quite yet purged out all of the NH3 that is produced in the dissolution of the urea, we have some ammonia in solution right now too, or to be more proper, we have ammonium hydroxide in solution. The ethylenediamine, I guess, should not smell ammoniacal whatsoever, or if it does smell like it, even just faintly, I guess that's okay. That means that you're going to have some contamination with ammonium hydroxide. But as long as the musty smell is overpowering any ammonia smell, then I guess we're okay. So after we distill it, we then acidify it, crush out any completely insoluble salts that may be in there, rehydrolyze it, and then fractal distill it. And so between the purification steps and the fractal distillation, I am pretty damn confident that we are going to be able to get, I would say, an 80% or better yield of ethylenediamine here. So this is what we were left with here. I took two fractions. This one you can see between 79.4 to 101. That was actually up to 102. I don't know why I put 101 on there, but that should say 102. But that's what that is, and there's, you know, maybe 10 mils in there. And then distillation stopped, and I think it was because of the setup I had, as I explained in the video. But this is the other fraction that I collected, and that's the highest that it went. Actually, the highest it peaked at 102.6. But I wrote this on the bottle a little prematurely. So this is 100.3 to 102.6 fraction I got, and this is 110 milliliters right here. And since we followed the protocol that we set out in this post on Science Madness, they claimed that they got 20% solution determined by titration of the ethylenediamine. So we're going to assume that this is 110 milliliters roughly of 20% concentrated ethylenediamine here. This is the flask that I was distilling out of. You can see that I got it pretty much to dryness. I mean, there's a little bit of shininess left in there that you're seeing, but that's just, you know, basically condensation. There's nothing left in there. So I would expect that if you're going to not try this at home, you won't get the same results. And that's it. This was ethylenediamine synthesis from ethylene glycol and urea. Hope you all enjoyed. And until next time, see y'all.